Dear students, this is Olga Savina, and this is our second laboratory experiment, a molar mass from freezing point depression. The freezing point depression is the one of the colligative properties of solutions, which means it does not depend on the nature of the solute, but on the number of solute molecules in a given quantity of solvent. For example, calcium chloride is preferred to sodium chloride for treating icy roads because of the effects of freezing point depression, as calcium chloride releases one more particle than sodium chloride does. It depresses the freezing point of water further and thus melts ice at lower temperatures. In this lab, we will measure the freezing point depression that occur with solutions containing a solute whose empirical formula is known. Then calculate the molar mass of the solute and its molecular formula. So the concept of the experiment. We will use the following apparatus, which is shown on the figure 2.1. And this apparatus consists of the beaker filled with ice and water, and also with a test tube, a thermometer, and a storing rod inserted into the test tube. So we will use the formula delta T is equal Kf times Cm. Delta Cf is the freezing point depression. Basically, this is the difference between freezing point of solvent, pure solvent, minus freezing point of solution. Cm, this is the molality of our solution, which is defined as number of moles of solute in 1 kilogram of solvent. Kf, this is the freezing point depression constant, and for the cyclohexane, which is our solvent, it is 20.5. So as I said before, the solvent is cyclohexane, and solute is a substance whose empirical formula is C3H2Cl. Okay, so to determine delta F, we will measure the freezing point of pure cyclohexane and the freezing point of a solution, solute in cyclohexane, and obtain it as a difference, as I said before, of temperatures. The freezing point of pure solvent minus the freezing point of solution. Method. To evaluate the freezing point of a sample, you will cool it and measure its temperature as a function of time. So let's observe these two curves. On the left side, it's a typical curve for cyclohexane. The freezing point is Tf, the constant temperature in the middle of the cooling curve. Here is the value of it. And on the right side, it's a typical curve for a solution, solute in cyclohexane. We have to draw two straight lines to describe the data immediately before and during freezing. So it's going to be one line before and during freezing. And the intercept will tell us about the freezing point of our solution. It is important to stir our solution properly. Otherwise, we will get the following curve. We will get the series of stair steps instead of smooth decrease in temperature. So in this case, the experiment should be repeated. Okay, let's go over the procedure. First, we have to obtain this apparatus. And also we have to know that all solutions containing cyclohexane should be discarded in an organic waste container. Also, we have to remember that hexane is flammable. No open flames in the laboratory. And this experiment will be conducted in a fume hood. Okay, our first step, we have to pipette 20.0 milliliters of cyclohexane into the apparatus, which means we have to pipette it into the test tube with the thermometer inserted and the stirrer, and this is our arc. So we have to have our sample in this test tube, and then we have to close it immediately. So second step, we have to calculate the mass of cyclohexane. Density is given to us, so how we can do that? 20.0 milliliters times 0.779 grams per milliliters. And then we will get our mass in grams. To convert it into kilograms, we have to use a conversion factor when 1 kilogram is equal to 1000 grams. We cancel grams and find our answer in kilograms. This is how we will do these calculations. So then we have to place the apparatus in a beaker that contains water and ice. So here's our beaker with water and ice. And again, we have to stir the cyclohexane gently and constantly. After temperature has dropped to 15 degrees Celsius, we have to start recording the temperature to the nearest 0.1 degrees Celsius every 15 seconds. The total time it's about 5 or 10 minutes. After cyclohexane has frozen and temperature has begun to decrease again, we have to remove the apparatus from the beaker and allow cyclohexane to melt completely. So the second trial, we have to repeat steps 3 through 6. Then we have to plot data and find freezing point of pure cyclohexane for both trials, and then calculate the mean freezing point of cyclohexane. We have to use the same cyclohexane for the second part of the experiment, so we don't have to pour it off the test tube. For the second part, we will measure the freezing point of solutions, and we will do 2 trials. First, we will obtain 2 pieces of weighing paper and record their masses to the nearest plus minus 0.001 gram. Then, for the first sample, we will place about 0.25 grams of the solute directly on the paper and record the mass of the paper and solute. It's going to be our first sample. Second, we will place about 0.11 grams to the solute directly on a second paper. Record mass of the paper and solute. By subtraction masses, we will find the masses of our samples. So then we have to transfer our first sample, which is this one, 0.25 grams, to the apparatus and stir it until it dissolves completely. Then stir solution gently but constantly. We have to cool this solution to 15 degrees Celsius and then record the temperature at 15 seconds intervals and continue until the entire solution is frozen. Then we have to remove the apparatus and allow the solution to melt completely. Plot your data. For the second trial, we have to add this amount of solute into the same test tube, and use it for the second trial. So the total mass for the second trial will be the sum of the first and second samples. And so we have to repeat our measurements, steps 6 through 9. Then we have to plot data for each sample to determine the freezing points for these two trials. Finally, we have to calculate each delta T using the method obtained in figure 2.3. So that means we have to plot our data and draw two straight lines and find the intercept and find the freezing point of the solution. And finally, we have to calculate the molar mass of the solute from each. Report your answer to an appropriate number of significant figures and obtain the mean molar mass. And after that, you have to determine the molecular formula of our solute.